Welcome to Programming in Modern C++. We are in week 9 and I am going to discuss module 45. In the last two modules, we have been discussing about C++ standard library. Specifically, we took a look at generic programming, and in the last module, we discussed about certain common properties of STL and its use in terms of the containers, useful containers that we have. In the present module, we will summarize the containers in STL. Certainly, we are not going to discuss each container at depth as we did for vector or map, but we will summarize and show you the commonality between them, and we also take a look at few important other library components we are associated for the use with the containers and even otherwise. Here is the outline which will be available on left. So, let us try to take a overall view on the data structures or containers in C++. So, containers are data structures in C++ standard library. They are ready made and they will work completely as a data type. That is a very, very important thing, that they are not just data structures as in C, but they are data types. So, anywhere you can use a built in data type, you can use a container. So, that is the kind of parallel that happens. And the varied element types can be really varied, including of course, user defined types, built in types and so on. So, a container is a holder of object that stores the collection of other objects, right, depending on the underlying type, and they are typically implemented as class templates, which allow the great flexibility of types that are supported as element. Right. It manages the storage space, it provides member functions to access, and it supports iterators. Now, you know that supporting iterator is very, very important to use the container, because that is the only way you can write algorithms for the different containers. Okay. Now, there are containers are kind of classified in certain, subclassified in certain ways. Vector, list and DQ are known as sequence containers. Vector, you know, list is doubly linked list, DQ is double ended queue. Typically, I mean many people pronounce it as deck. So, as in a queue you can add at one end and remove element from the other. In stack you add and remove elements from the same end. In DQ you can add and remove elements at both ends. So, that is why it is called doubly ended queue, right. But they keep the elements in a physical sequence. So, they are called sequence containers. Then we have associative containers. Associative containers are those like in map, where you have a key and a value associated with it. So, here in a sequence container, you find out the value based on certain position in the sequence, either through indexing or by or by traversing the list, or by adding and taking out elements from DQ and so on. But in an associative container, there is an association between a pair of values. So, given one you find the other. So, that is why it is called the associative container, and map is the most useful associative container, or the most useful container after vector, which can associate any key type with any value type. Set is another, which is a collection of value items which are unique, right. So, it just allows you to have unique set of elements, right, which is very important, and you can do typical set algebra with that. Multi-map and multi-set are relaxations on the map and set, where you have allowed duplication of elements. Like map will not allow duplication of key, but if you want duplicate keys with different values associated with them to be present, then you can use a multi-map. Similarly, you can use a multi-set. In C++, we will see there is also things like unordered map, which is basically hash table or unordered set, because even though we do not say in terms of the associative container, the underlying implementation of these containers do need an ordering, and since they do need an ordering, the element type should be such that the ordering should be possible, they should be comparable, right. But in unordered cases you would not require that. And many are called almost containers. Primary of them are container adapters, which are not a total implementation of containers, but those are implemented on other containers with certain additional property, right. So, you have stack in that, you have queue in that, and you have priority queue in that. These are container adapters. So, they have an underlying container which is not necessarily always specified, and based on that, so that container gives you the basic container support, but there are specific functionality that you implement in terms of the member functions in the STL that gives you the stack component, queue component, and priority queue component. So, these are called almost containers. So, is string because it's kind of a vector, but its element type is always character. So, it's a kind of a almost container. General arrays that we have in the language is a almost container. Bit set is where we keep the bits, is an almost container, and so on. And in C++11 we will see that the standard library will also have a component call array other than the language array, and that array is different from the vector, right. We will see that fun, right. So, these are the, so this is a complete chart of the containers in the standard library. Just for convenience and easy reference, you remember my one slide summary principle. So, this is a one slide summary of the containers that you have in C++, including C++11. So, those which are only in C++11 I have marked them, and what you can get to see is what is the class template for the each one. So, which basically say what is the functionality that this particular container will have, and here are some remarks that are available, like for stack the underlying container by default is a DQ, whereas for a queue it is also a DQ, whereas for a priority queue it is a vector. But the design is such that if you want, then any other type of underlying container as specified can also be used for these container adapters. Now, there are different properties, basic properties that I have tried to summarize here. So, you have the sequence containers 3 in C++03, 2 more in C++11, 3 container adapters, 4 associative containers, and 4 associative unordered containers in C++11, right. So, this is the total set. Of course, you do not from day one you do not start using all of them. It is primarily the vector and a map, then possibly list, stack queue is what will be most of the use that you will find. These are just showing you the template template styles of these different containers in C++03. I am not going through them, you can read them, study them, and the basic principle you will have to remember is of uniformity. So, do not try to remember anything, but try to understand the reason of why it is so, For example, if I look at say map, I am looking at map, right. So, class key obviously is the key, this is T is the map type, and I have a compare. Why? Because as I said, map is an ordered container. To represent the map in the underlying way, it is using a binary search tree which needs ordering. So, I need to have an ordering on the key value. So, I am using the less functor with the key value type for doing this. What will be the allocation? Allocation is allocator is basically the underlying container that you use. So, this is the type of the allocator that you will have. It will have a key, constant type of key and the map type paired, and allocation will happen on that. So, once you understand this, you will understand that it is relatively easy. You do not have to really remember anything, but things are done in a very uniform manner. Right. For example, in case of container adapter stack, it is saying that the class container, the second parameter is class container, which is defaulted by DQT. So, if you just say stack int, what have you specified? You have specified this T as int. So, your stack will actually be implemented, you will get a code that is implemented on DQ int, deck of integers. But if you want something else, you can pass a second parameter to your template instantiation of what type of underlying container you want, and you will get that type of container. So, that is the kind of flexibility that STL containers give us, that is the kind of uniformity STL containers give us, there is a kind of power STL containers give us. So, these are the different member types. Value type you have seen already number of places, allocated type is what kind of allocation will happen. Then there is reference type, pointer type and so on, iterated type we have seen, key type, size type. So, this is typically what maybe some containers will not need to define some of these, but most containers will define most of these member types. So, you know conceptually that over all these 10 containers it is all uniform in terms of. So, these are the types that you can use the container type name vector int colon colon value type, or so you have that type, you will be able to see what is the value type that you have, what is the size type that you have. Coming to the operations, I have tried to do a uniformity summary. I was looking for it, I did not find it anywhere. So, I built it from the manual. So, on left you see the containers, and these columns are the types of different operations that are available. So, one is capacity related. So, vector has 3 capacity related members, resize, capacity and reserve, whereas deck has only one, list or set etc., they do not have anything. Whereas, if you look at say modifiers, you will find this as a push back, pop back, that is you can add at the end, take out at the end. This is push back, pop back, but deck is at 2 ends. So, it has push front, pop front, list is at both ends. So, it has all of these. Right. So, assign is available for all of them, you can assign each one of these data structures. So, you can see that there are different, if you just think conceptually as to what the data structure should give you, you will find that those operations would be available appropriately in that STL container type. So, here that is some more of these, some we have already seen, and like if you look at the container adapters, you can see a very uniform design, all have empty, size, stack has push pop, queue also has push pop, priority queue also has push pop. In addition, to keep to the naming conventions used in queue, it also has front and back, right. So, these are different kind of operations that you can think of. So, kind of that was a summary picture of what you have in terms of containers in STL. Before we close on STL and the standard library, let me just take you through some of the other components like algorithm. Algorithm is a component, a header which defines a collection of functions which are designed to work on a range of elements. Where do you get a range of elements? By iteration, right. So, that is how algorithms can work on any container, right. So, it is naturally STL style. So, it takes one or more sequences and one or more operations and performs. Naturally, there is a large number of algorithms available, but some are like find is BEV written in short form. So, that I should give a lower annotation also, I can give that, but it is quite obvious. B is the begin iterator, E is the end iterator, V is the value. So, you are doing a find, you have already seen that find V, begin, end, predicate, right. Similarly, count, it counts how many are there of that value V and so on. So, find, count, sort, copy, unique copy, merge, these are some of the very common algorithms which will be available in this component. Just to see an example say of copy. So, we can copy the elements from a range of first to last to another iterator starting at say result, right. So, it has to take two iterators, one is the input iterator from which you are copying and another is the output iterator to which it goes. So, the output iterator finally is the result that you return. So, in the input iterator you get the first and last, output iterator you just have the result where you will copy, right, the destination. It is quite simple as to how the code will look like. It is, you do not need to write this because it is available in the algorithm component, just include that, you will have a copy. So, here I have defined a list of int and a vector of double, and I have made the size of this vector same as that of the list because I want to copy in that. So, I am copying elements from a list of integer to a vector of double, and just see how easy it is. First I will check if the vector is large enough, if it is not, then certainly I cannot do, and then copy is just a one line code. This is the beginning iterator of list, ending iterator of the list. So, this is my list and this is the beginning iterator of my destination, output iterator, the vector where I will copy, right. So, once I have done that, it is all available. I can assign this to get the final iterator if I want to use it. I have directly used the vector itself and I have sorted it using the sort function which is also available in the algorithm. So, once I do that, naturally you can see that how easily things can be copied and sorted using the algorithm component. There are very interesting numeric component available which can also be used in semi numerical context. So, the numeric header basically has had in C++ 03 it had four different algorithms. In C++ 11 one more has been added. So, of these I will just take example of two and show you. First is accumulate. I really like this because what it does is it basically you can think of that I have a collection, I want to take the elements and add them, right. So, it simply does that accumulate. So, the iterator class as input, the element type to add. So, your actual function is the first and last iterator, and the initial value, because you need to, you are accumulating. So, are you starting with 0 or starting with something else? So, that tells you the element type, and this certainly is, this is your iteration loop, which is by now you know it is almost common across all different algorithms. This is the way to go to the next element, this also is known. So, this is my accumulation code. You take the element star first, add it to int, put it back to int. So, that is a beautiful logic. Now, before getting into the next one, let me just show you the use of this. So, this accumulator, with this accumulator I have created a vector and I accumulate begin end. I have passed 0 as the initial value, right. So, starting from 0 all will be get added 1, 2, 3, 4, result is, if you print sum you will see 10. I have another vector of double, and I have written a function which takes a vector of double, it takes a int pointer and it takes a number. So, just to show the different ways of working. So, in the vector of double I pass VD, in the int pointer I pass this vector by the address of its 0th element. This is the address of its 0th element. I pass it here. So, it is coming as a integer pointer converted, and then how many elements are there in that vector. So, as I do that inside this I can accumulate. If I pass 0, it will accumulate in the integer way. If I pass long 0, it will accumulate in the long type. If I pass 0.0, it will accumulate in the double type, and so on. So, all these are possible. I can also pass my accumulation variable and then reassign it here to get the accumulation done. So, it can accumulate everything, right. That is a nice way that you do not need. But the more interesting part of this story is that you can actually, I have actually come back one slide. You can, if you notice here, then this is just an operation of addition being done. It is an operator, right. So, with all our notion, I can say that this is nothing but operator plus working with init and star first. Right. So, it is possible that I would not hard code this operator plus, rather I will pass it to this algorithm as a function object. So, I put another parameter binary operator, I put another parameter to this accumulate function also, and I pass an op, which is a binary function object, right, which certainly has to return an appropriate type of value, which is same as t. So, then this generically is changed to op applied onto init and star first, and that will do the job. Now, if I pass operator plus, of course, I will not, because I have the default accumulator. If I pass operator plus, then I will get the first behavior, otherwise I can pass anything, I can pass an operator multiply, then the values will get multiplied, right, as nice as that, the same code. So, let us go and see this. So, I have this accumulate, this is a list of list L of integer 1, 2, 3, 4 I have defined, and then I am calling this function with this list. I have begin and end iterator. I am initializing with actually I should initialize it with 1, 1.0 is not needed. Initialize it with 1, and then what I pass as an operator is multiplies. Multiplies is a standard function object, which is a binary function object which takes two parameters of the given type, multiplies them and returns back the result. So, it is a binary multiplying operator. Right. So, I pass the multiplies. So, what will happen? Now, instead of adding the elements as they come from the iteration, it will multiply the elements. So, it will multiply 1 with 2, then with 3, then with 4. So, the result will be 24. Right. So, these are, and I mean this is just a simple illustration. You can write your own functor to pass here as well and do anything as you accumulate the values. The accumulation can be done in terms of components of records also. Suppose you have a record which has unit price and number of units, and you want to see what is the total price, total value of the collection. Right. So, for every case, every record in that collection, you will have to multiply the unit price with the number of units and add them. Right. So, it is not a matter of one operation, but it is a multiplication then addition. Right. So, you can define it in terms of a function and pass that function pointer. Just remember, anywhere you can pass a function object, you can also pass a function pointer, or better still, you can define a lambda which is a function object. There is an anonymous function with the same code as this one and pass it to the accumulate. It will accumulate the entire value. The advantage of doing this is, of course, since this is a simple code, the advantage of doing this is whoever is reading it can clearly see what is being done, very understandable. An anonymous function we will see more in C++ 11. So, these are some of the different things that accumulate can do. Let us look at another inner product. Inner product is something in school, high school you used to do, vector inner product, that is you are given two vectors and you do component wise multiplication and then add them. But now for us it need not be a vector, because everything through the iterator can be thought of as a sequence. So, it is a corresponding elements of the sequence, those will have to be multiplied and added together. So, a inner product component, inner product algorithm will take an iterator first and last of one sequence, one iterator in, then it will have another the other one, the other vector or other list that you are doing inner product with. You do not need the end of that, because when this ends, that has to end, because unless they are of the same length, inner product is not defined, and the initial value. So, kind of the price unit price part we were doing can be directly done by this. So, you get the element pointed to by the first iterator, get the element pointed to by the second iterator at two different vectors, multiply them here and add, accumulate. So, this gives you the inner product. So, you can see there is a very naive example I have given. These are different prices and there is a different weights of the index, and so you do price begin, price end and weight begin and find the inner product to see the entire value. Interestingly, like you do for like we did for accumulator, we can generalize the inner product also, but in inner product there are two operations. What you are saying? You have sequences, you are taking element component wise, each element, multiplying them and then adding them. So, this is operator plus init, then it's becoming cluttered. Let me write clearly. Operator plus, then init, then operator star, then star first, then star first 2, right. This is the meaning of this expression, right. So, there is nothing special about operator plus and operator star. I can pass 2 functors. So, the generic form of this actually passes 2 binary operators, 2 binary function objects, and does this as a total generic binary operators of any 2 types. So, you can do inner products. For example, I can define interestingly I can define that I will take element wise, add them, and then added values I will multiply, whatever that means. So, anything of that sort is available. So, you can see the power of STL gives you it's a lot of flexibility and generality of what you can do with the data with the containers. The functional component is another very important, which basically defines a set of function objects. So, these are used typically as arguments to functions such as predicates or comparison functions and so on. So, there are many useful standard function objects like plus, minus, multiplies. We have just now we have used multiplies, right, divides, modulus. So, the basic arithmetic operators, the basic your comparison operators, logical operators, those are available in terms of the functional component. So, when you are making use of STL algorithms, you can make use of these function objects to ease your task. You do not have to write them, but a much bigger value of the functional component comes in terms of actually building up bigger components, more powerful components in terms of building up closure objects and so on and so forth. So, there are some like there is a template called function, which allows you to define the prototype of a function having certain input parameter types and a given result type. So, you can write something like function int, I am sorry, this is function, this is you can write something like this, which will mean that this is the type of a function which takes 2 integers and gives you an integer result. We will see more of that. We will see ways to bind variables, parameters to functions and so on. So, these are heavily used in C++11. So, though at a basic level the support is also available for C++03, I chose not to discuss them here, because it would be better to discuss it once when we discuss C++11 standard library as a whole, right. So, that brings us to the closure of the discussion on the C++ standard library. I have obviously, while I have tried to summarize the containers extensively, because I feel the containers, iterators and associated algorithms are the most useful, but we have been able to glimpse through only some of the algorithms and functional particularly partly, and there are a number of other even besides the IO related ones, there are a number of other components as well, which are less frequently used, and you will once you learn the style of STL based standard library use, I think any other component you will be able to learn by yourself very easily. Thank you very much for your attention. This brings us more or less to the closure of C++ 03 discussions. The remaining 3 weeks we will really spend on the modern part of C++, which will be C++ 11 and at times C++ 14, C++ 17 and so on.